So in this video, I'm going to explain all types of logistic regression, including the assumption checks that we need to investigate before running logistic regression. Depending on your analytical approach, you may have freedom to choose any of these types of logistic regression, especially if you have different types of your dependent variables. Like here, like I have like a 2 level of depression here, that is clinical versus non-clinical. And I have a 5 level of depression level, that is mild, normal, severe, extremely severe, moderate. And so, for example, if I want to choose this approach, I can just choose binary logistic regression that is very related to my binary categorical dependent variable. And also, I may consider multinomial or ordinal levels of logistic types of logistic regression. And can do that also together if I want to consider this version of my dependent variable that has more levels. So that doesn't mean that you have to do all these types of logistic regression together. But there are some certain assumptions that are applicable to all types of logistic regression, disregarding of the specific types that you want to include. The first one is what I just mentioned, that your dependent variable should be a type of categorical variable, either binary categorical variable, multinomial categorical variable, or ordinal categorical variable. Let me explain that a little bit more when discussing each of the logistic regression type, because each one suits better a type of logistic regression. But the general fact point is that your dependent variable should be categorical. It cannot be continuous. And the second assumption is lack of multicollinearity. Lack of multicollinearity means that there should not be a high level of correlations between independent variables or predictors in your model. And it's only just independent variables. Like, for example, I have 4 continuous independent variables. They should not be highly correlated. In JASP, it can be checked directly when you run your main analysis for binary logistic regression. However, whenever your main analysis cannot directly investigate this assumption, it can be checked through bivariate correlations between predictors. For example, like using the options of correlation here that I explained in another tutorial video. In this case, if all of your independent variables or predictors are correlated with each other, but it's less than 0.70%, that means that the assumption is met because they are not highly correlated. However, if there are 2 predictors that have a higher level of correlation with each other, like for example, 0.80, 0.90, they should not be included in the same regression model together. That means that you may need to run different regression models, each time with one of those highly correlated variables. So this is the second assumption, lack of multicollinearity, that can be checked simply with a correlation, bivariate correlation, or can be also the binary logistic regression in JASP also can directly check this assumption. So that means that if you are going to use binary logistic regression, you don't need to run separate bivariate correlations to check this assumption. The other assumption is the lack of influential outliers. So again, if you are choosing a binary logistic regression, this assumption can be checked with running the main analysis through a measure that we call Cox distance. So I will explain this later when showing the main analysis for binary logistic regression. However, if you are using ordinal or multinomial logistic regression, you need to use the strategy that I explained in the descriptive analysis tutorial about how to detect potential influential outliers. Because for those types of analysis, checking the influential outlier is not by default included in your main analysis. So you should do it based on the descriptive functions like here, as I explained in another tutorial video with the title of Descriptive Statistics by Variate Correlations. And the next assumption is independence of observations. This assumption is very similar to the same name that you potentially have heard about the multiple linear regression. That means that there should all of your participants in the data set should have only one point of data, and there should not be any duplicate. Unfortunately, there is no statistical measure to assess this in logistic regression, although we have some statistical measures for multiple linear regression for that. However, when you want to check this assumption for logistic regression, uh, if in the process of data collection and data cleaning, you had some strategies to check and double check that each participant only had one data point in the data set, that means that this assumption is met already. For example, when using Prolific for our data collection, this platform can safeguard that this assumption is met because this platform can limit each participant to participate only more than once in our research. So we can also visually inspect the data during the data cleaning process to make sure that no participant has duplicate data or more than one data. And so this all can sort of safeguard that the independence of observation assumption is met. And the final assumption that is actually can be a little bit time consuming to test is the assumption that we call logit linearity. This is similar to the assumption of linearity for simple regression, but within the context of logistic regression analysis. Since our outcome variable is categorical here, a simple linearity test does not apply, cannot easily apply here. So we need to do some transformation in our continuous predictors to be able to check linearity in the context of logistic regression. So we can do this. The method that I'm going to show you now is in some textbook is called Box-Tidwell check methods. However, you don't have to necessarily refer to this. You can just describe the process that you do to test this assumption. So we are going to test now the assumption of logit linearity. So for testing this assumption, what you need is to have some transformation. You need to transform your all of your main variables into uh, a transform version that can allow you then to check the assumption of a logit linearity. So for this option, you use this icon, like plus icon in JASP. And for example, you can name it whatever you want. But for example, I want to do it for my IV4. And I'm going to use just this name, like like for example, IV4, just I know that it is about IV4. And I know that I want to make an interaction term for IV4. So I name it, I create it as a new variable, and then you have this here. So here, what I need to find IV4 because I wanted to do that for IV4, and I want to make an interaction term. So I need this symbol to making an interaction term. And I want to make an interaction between each independent variable and its natural log. So I have the independent variable that is IV4, but what I need to do is look for the natural log for IV4. That is actually the here, the log of IV4. So, and here I can have because it should be the same variable, so I'm going to drag IV4 into log. So everything is now fine. So I have IV4 interaction with natural log of the same variable that is IV4. And now it's ready to compute column. So now if I close this, you can see that I have now a new variable here that is actually the interaction term that I need to test the assumption of logit linearity. So I have done it previously for the other variables. So you should repeat this process for each of your independent variables that are continuous variable. So I have done it previously for IV1, 2, 3, and I just left the IV4 to do it now to show you how to do this. But in action, you need to do this beforehand, unless in the process of data cleaning, it has already been done. Like for example, the data set you get may already have these values, and then you can skip this transformation step. So assume that it has already included in your data set, and then what you need to do is to quickly run your main analysis, but not with the purpose of running the analysis. So now you need to include both your original IVs and the interaction terms as predictors in any model of logistic regression that you want to test. And if the results, the coefficients are not significant for these interaction terms, then you can conclude that the assumption of logit linearity is met. I can show you quickly how to do that. So for example, imagine for like logistic regression, like binary logistic regression, I want to test this assumption. So I go to logistic regression, and so my DV is like the binary version of my depression that, and also my IVs are these four IV that are my main IVs, but no, I'm not going to test my analysis now. I just want to check the assumption. So I also add these interaction terms that I just created in addition to my IV to the model as additional predictors. So all I need, I don't need to set anything for a statistic because it's not my main analysis, it's just for assumption check. So what I do, I go to the coefficient table and I see the significance for these interaction terms, not the main effects, the interaction terms only. So as long as I can see no significant p-value for interaction terms, that means that the assumption of logit linearity is met. So that's all you need to do. For other types of logistic regression, the same. You run the logistic regression and include all the IVs and the interaction terms for IVs together. And if the p-values are not significant, that means that the assumption of logit linearity is met. For example, I quickly can show that, like, how does it look like for other types of logistic regression. For example, for multinomial and binary also, I can show you that I have all my IVs. And in addition to that, I add all of the interaction terms to the IVs. And I will explain this for the your main analysis later, but I just want to quickly to show you where to look for assumptions. For example, again, the table of coefficient, I just look for interaction terms. As long as there is no significant results, that means that this assumption is met. And if I change the test to it's multinomial, I change it to ordinal again, the same. I just look for the interaction terms and I want them not to be significant. For example, I see one is significant here. So it means a slight violation. That if you have situations like this, one point is that you check multinomial, and if multinomial is okay, ordinal is okay, just the ordinal is not okay. So that means that again, with a lenient approach, you can say that the assumption is met. But also big sensitive is very close to being non-significant. However, if it's in your actual data is consistently significant in different types of logistic regression, then usually if you transform your original variable, for example, you see that the problem is for IV1. If I go and transform my IV1 and then consider the transform version of my IV1 and do all the steps that I just mentioned for this assumption check, like I consider the transform version of my IV1 and consider the interaction term for that transform version, and then check this assumption again, I may see that this can turn into non-significant result. But this just in case that you have any obvious violation from this assumption. So for now, I can just kind of assume that there is no violation for the assumptions. And coming back to the data. So that was the last assumption that I wanted to check for logistic regression. If all are good, I can run any type of logistic regression. There is just another assumption that is called the proportional odds or parallel lines that is specific to ordinal logistic regression, but unfortunately JASP doesn't have any option to test that assumption. So it's pointless if I discuss it here because it's not included in JASP in that. You can test that assumption only if you use SPSS or other software. So let's start